What's up, guys? Mr. Adams. So we are kind of done with the inheritance and stuff. So we're going to move on, and we've actually moved on a couple times. If you guys were in person last week, we did this. So we're going to do it again. If you weren't in person, so I'm going to explain it again. So if you feel like, oh, yes, I get this, then you can skip this and you can just go ahead and do some. If you haven't seen this before, then you want to pay attention. In recursion is like way hard. Like there's kind of two ways you can do this. One, you can kind of get the system down, and then it kind of magically you start understanding it, or it's the other way of you kind of, well, I don't know. I think that's the way it works. You're just going to kind of, once you kind of understand how it works, then understanding why it works makes it a little bit better. Okay, so kind of the idea here is that if I want, well, if we do this, if I were to write this out, it's going to be red here. I'm going to just use my finger, I think. Let's see. Yeah. Erase. Okay. So if I have 9, whoops. If let's say n is 3, that's an easy one. So I go 3 times 2 times 1. So I'd have to go n times n minus 1 times n minus 2. And then I'd have to figure out how many n's I have, and the number of n's would tell me how many times to subtract, and then it gets really confusing. Okay, so I could do this a different way, which is I could go f of n, right? So anyway, that way it's maybe not the best. Well, this one doesn't work quite as good as the next one, so we'll show it a different way in a second. But the idea is if I put the same function in several times, then I can deal with this way easier. So if I have numbers either going up or going down, recursion is the way to go rather than just kind of manually doing it. So this is a good example, although it's not the easiest one to follow. So we're going to do this one, and then the next one's easy. I don't know why I'm erasing that. All right, so here is how recursion works. So recursion, you need a kickout point. I need a finishing point. So at 1, this is my finishing point. So I'm going to say if n equals 1, okay, and I'm going to return 1. And you're always going to have, you have to have a stopping point. Kind of, I like to think of it as you're zipping up. So you kind of got this is where I start zipping. Okay, so the 1 is where I zip. And then if it's not, I'm going to return. And then I have n times factorial n minus 1. And you're like, wait, how does that work? Because you can't put something inside itself, but you can. Because what we're doing is we're building up this I don't know, this one equation. We're doing one equation all at once with the variable n every single time, and then at the end we zip through it. Okay, I think if I wrote it out the long way, it'd still be just as equally confusing. So anyway, so we build this up, and then when n becomes 1, that's my zip up, and I zoop right up all the way. So I have my kick out, and then I have my I'm always going to return. So the deal with recursion, there's 2 things that have to happen. 1, I have to have some reason to stop, and 2, I'm going to have to call my my function, my method, I guess better, my method every single time. And then 3, then I have to have a reason to go down. So if this doesn't magically turn into this at some point, then we have a problem. Okay? All right, so I run it, loop, and I think I do have to erase all that gunk because it'll probably be on my next screen. Boom, we got it. Now, if you're like, whoa, that was pretty easy, I understand that. That's okay because we'll move on. And that's seriously like you just, once you do a ton of these, they start making sense a lot more than, it's just like you kind of gotta do them. You gotta cheat a little bit. It's fine. Don't cheat all you want. If you cheat and say, oh, this is actually how it works, and then the next one you try and apply that, then you're okay. All right. So then we shall do the next one. Oh, you guys can see the answer. I already did these. I forgot. Close your eyes. Okay. All right. And then, spoiler, I have it up on the screen next to me. Okay. All right. So bunnies. And the bunnies one is a little bit easier to actually see what we want because I have kind of easier, but not really. I'm not going to worry about writing this one out either. Because this one you can kind of think of a little bit more. Because each time I add a bunny, I just add 2 to it, right? So if I have, I have a bunny, 2, another bunny, another 2, and so on and so forth. So I'm just adding 2 each time. This one, 100%, you can do multiplication wise. That's totally get that. We're just learn crawl first, okay? So first of all, we always need a kick out. We need a reason to stop doing what we are doing. So this case, it's 0, and it's usually, especially when you're doing coding bat, they usually tell you the first one or whatever, whenever we want to kick it out. Okay, so we say if n equals 0, return 0. All right, because no bunnies, no thing. All right, okay, so then oh, also, we've kind of gone past, we don't need the squiggle brackets because it's just one line. And the recursion is kind of a good way to that's going to happen every single time. All right, so then we want to return 2 plus 20 years and minus 1. All right, so, oops, and I already messed up a little bit, okay, because we don't have an n anywhere in here. So 1, I need to change this word to bunnies. And then this to bunnies as well. What just happened? Okay. All right. All right. So once again, I got my kick out and I call my function with 1 less each time. And I mean, that's kind of where the just kind of learning the tricks goes. All right. So zip it up. Whoop. All right. Going through. So right now, if you're like, if today all we get to is you getting the little tricks to it, but not quite understanding it, still all magic, you know, that is fine. That's kind of the goal today is just be comfortable with the form, be comfortable with this is the one step that we do, this is the next step. All right, so I'm going to do one more. I'm not sure the answer. Keep your eyes closed. All right. Okay, so Fibonacci is a good one to write out because I have 0 and 1. 0 plus 1 is 1. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. And then so on and so forth. If I think of it this way, it's n. This would be n minus 1. So then the next one, this would be n. This would be n minus 1. And this is and this would be n. This would be n minus 1. So we can see the pattern each time we're adding the next 2. So you kind of need to know where to stop before you can go to the beginning, okay? And if we were to say, like, for instance, if you were to say, well, what's the Fibonacci number for the first 10 digits? The only way to do that would be add each time. Like, you can't just multiply out and figure that out. So this is where recursion actually works really well, is if you have things like this that depend on the other ones. And we do this, we used to do it in Algebra 2, but now I don't think they do when I taught, and I can't remember what it's called. Because there is a way, like you can figure out the difference each time, and then you can divide. Ugh, I don't remember what it is right now. And I don't think you even do it anymore. So anyway, well, you guys probably doing the honors, but it was probably a long time ago. Alrighty, so we need to know when to kick out. And here, the problem is we need to kick out at least, we need to kick out a couple of times, because if it's 0, oops, if n equals 0, we want to return 0. Okay, and then, but the problem is that's not the only time we want to just magically kick out something. Okay, so we also want to kick out something if n is 1. So if n equals 1, return 1. Okay, so I have to look, and then really, I mean, I could do this for all of them. We don't need the 2 because we already have the 1, and then 0 plus 1 is 1. And then the other thing we need to make sure we do is, well, when I show you this, we got to make sure we cover all of them, because if we don't do this one, if we just do this as the stopping point, first of all, we could have a 0 and then it would break it. And then 2, I'll show you when we get the answer. All right, so we need to think the answer, and I should have erased it, 21 is the next 2. And I kind of wrote that down wrong. So 21 is 13 plus 8. 13 is 8 plus 5. So when I return this, I want to return the 2 previous numbers. So I want to return Fibonacci n minus 2 plus Fibonacci n minus 1. All right. So then here, I also need to make sure that I never reach the n minus 2, because if I have n equals 1, then that's going to kick me out before. So I'm kind of really starting on 2. So if I n minus 2, then I get Fibonacci 0 and Fibonacci 1. All right. So we got to make sure that these 2 numbers kick out, or these kick out before these go negative. I guess if that makes sense. Okay. All right. So then I run this. Boom. Yes. Okay. So what I want you to do is I want you to try the next couple. Let's go next 4. All right, because they don't take very long once you get going. I was messing around. No, see now one gets freebie if you want to delete. Okay. Now these don't have the answers, but if you go like this and hit copy and then search Google, okay, the answers all show up. There's several places where you can have them and you can look, and there's even a video explaining it right there. Okay, so it is okay if right now you barely one little thread of yes, I understand this, and you're like, oh man, like I had to cheat on all of those. It's okay, because once you get it, you do get it, and it's pretty easy. Like, well, you're gonna feel a lot more confident doing it. When we do this after spring break, and I'm like, no computer, just write it all out. That's when it gets really hard. Okay. All right. So yeah. All right. Thanks.